Find the current ID using LCM equations of this NMOS transistor, given the following parameters. Threshold voltage equals 0.4 volts, transconductance parameter Kn equals 1 milliamp per volt squared, bulk threshold equals 0.2 volts to the 1/2, the MOSFET device parameter equals 0.1 volts to the -1, oxide capacitance equals 1.004 microfarad per centimeter squared, surface potential equals 0.88 volts, width equals 1 micrometer, and length equals 0.1 micrometers. First, we need to identify each part of this MOSFET. On the left side here, we have the gate. On the top is the drain. Bottom is the source. And on the right here, we have the substrate, which we will call the body. The body is typically tied to the lowest potential of the system, which was given to be -1 volts, which is actually lower than ground, which is 0 volts. Knowing this, we first need to see whether the device is on or off. If it's on, VGS is greater than VTN, which is not VTNO. First, let's find VGS, which equals VG minus VS. And we can see that the voltage here is 2 volts at the G node, minus the voltage at the S node, which you can see is ground, which is 0 volts. The difference between these two potentials is 2 volts. Now we need to see if body effect exists for this device, in which VSB doesn't equal 0 volts. However, you can see that VSB equals VS minus VB. And VS again is 0 volts minus the potential at B, the body, which is actually -1 volts. So it is not 0 volts and body effect does exist. So it makes our work a little longer. This equals +1 volts because subtracting a negative number gives you a positive number. Given this, we can calculate the actual VTN, which is VTNO plus gamma times square root of absolute value of 2 phi f in case it's negative, plus VSB, all within the first radical, minus the square root of absolute value of 2 phi f. See, if VSB was 0 volts, then these two terms would cancel out, multiplying that by 0 to the gamma, which would give you just VTNO. But in this case, VSB is 1 volt. So we will say that this equals 0.4 volts, which was given up here as VTNO, plus 0.2 volts to the 1/2 times square root of 0.88 volts plus 1 volt minus the square root of 0.88 volts. Putting this in the calculator, you get your threshold voltage of 0.487 volts. Now comparing that to VGS, we can clearly see that VGS is greater than VTN. Thus, the device is on. Now we must see what mode it's in. Using the variable VDS sat, if VDS is greater than this, it's in saturation, and if it's less than this, it is in triode, or linear, which is the same thing. Now VDS sat, which is under the long channel model equations, is simply VGS minus VTN. And that equals 2 volts minus 0.487 volts. And that equals 1.513 volts. Comparing this to VDS, which is VD minus VS, we can see VD is 1 volt minus VS, which is 0 volts, which is again 1 volt. And this, of course, is less than VDS sat, indicating that this NMOS transistor is in triode. Given the state, we can calculate the current, which I'll call ID since it's through the drain. And I'll add a little try to imply that it's in the triode state, and that equals Kn times VGS minus VTN times VDS minus VDS squared over 2. And that equals 1 milliamp per volt squared times parentheses 2 volts minus 0.487 volts times VDS, which we just found to be 1 volt, minus VDS squared over 2. So our final answer for this problem equals 1.013 milliamps, which is the same thing as 1.013 times 10 to the negative third amps. If you have any questions, please leave in the comments below, and good luck.